Man, I never thought I would be talking about this, at least on this show. This is quantum information is what I studied, what I got my master's degree in. I worked in quantum information, quantum photonics, quantum communication, quantum photonics, different than quantum computing, but it's all kind of under the quantum information umbrella. Quantum computers have gotten a lot of hype, so I thought this would be a great opportunity to kind of talk about them. I will say that this isn't as much about practical trading as more of a market awareness piece to talk about like what quantum computers are, why people care, what their limitations are. And then the second half of the segment is really just like trying to explain like what a quantum computer is and like why it has some of the levels of speed up that we've seen published by Google, for example. So the second half, I would say, is a little bit less applicable. It's more of just a way for me to kind of nerd out. But the first half is really more of a market awareness piece, talking about a little bit of the history and why they have gotten so much attention in media, and especially recently. Does that make sense?
Yes.
Hell yeah.
Yes.
Okay, introduction. So since the announcement of Google's Willow chip, we've had a couple other major milestones since then, but it seems like there was a big pivot around that announcement that happened in early December of 2024. There has been a lot more attention put in the quantum information space and quantum computing companies. So today I wanted to talk about exactly what quantum computers are, what their potential applications and limitations are, and maybe some of the timelines for this technology, but definitely focusing on the applications and the limitations a little bit more. Make sense?
Yep.
Okay, so a little bit of the history. Concept of the quantum computer was really popularized around the 1980s, early 1980s by Richard Feynman and Yuri Manin. But Richard Feynman, like very prominent physicist, obviously he's pretty popular physicist personality, I guess I would say, and absolutely brilliant. And there was obviously research and discussions around this technology before he kind of popularized it. But he was certainly one of the prominent personalities that made a lot more people pay attention to it, especially in the physics community. And effectively, the motivation was to find a better way or a more efficient way to perform quantum simulations or simulations of quantum systems, because these are incredibly resource intensive to do on classical computers. When I say classical, that just kind of means not quantum, basically. Yeah. So when I say classical, there's quantum. But as a way to sort of simulate quantum systems in a faster and more efficient way than on classical devices. And basically the idea was like, well, if we're trying to simulate quantum systems, let's use quantum particles to actually do that. And hence the quantum computer was kind of conceptualized. So there was research and development and major milestones that happened kind of since the 1980s. And one of the big ones was in 1994. And in 1994, Shor's algorithm was published. And this really put a much broader attention on quantum computers because this was a feasible application that was kind of outside quantum simulations. This was a more practical application with Shor's algorithm. And effectively what Shor's algorithm does, it's a quantum algorithm, which is, it sounds like kind of a lot, but it's an algorithm for quantum computers that effectively solves this problem called prime factorization. So prime factorization, basically with the number 24, this is an example of what prime factorization looks like. We have a number and we're trying to figure out which primes can be multiplied together to get that number. So for example, the primes for 24 are 2 and 3. 24 is a very easy to prime factorize, right? But if I go a number that's like hundreds of digits long and I tell you what are the primes in this number, that is an incredibly complex calculation to do on classical machines. And that is why it forms the basis for a lot of modern encryption. A lot of modern encryption actually uses prime factorization as a way to secure information. And this kind of works because, like I said, it would take classical computers like thousands and thousands of years to brute force break that encryption. And RSA is probably one of the most popular ones. It's very commonly used form of encryption, right? And this is founded on this prime factorization. But with Shor's algorithm, a quantum computer can factorize primes very, very, very. Because of this discovery, this put a lot more attention on quantum computers from realms that were kind of outside of physics. And then Grover's algorithm followed shortly after that. I believe it was 96. And this basically is an algorithm that handles unstructured search in a faster and more efficient way. So basically, when we have a database that's not really structured, we just have really, really large amount of data. Grover's algorithm can be used by quantum computers to effectively search information, kind of parse that data way, way faster than classical computers. So the potential to do that, I should say, because this is obviously an emerging sector and there's a lot of unknowns as we are starting to develop this technology more and more. But these were like two very big milestones that kind of moved quantum computing, for lack of a better phrase, outside of physics and into other industries and other disciplines. So these early milestones demonstrated that quantum computers have the potential to maybe execute certain types of calculations that are infeasible for classical machines to do, whether that's down to time, whether that's down to power requirements, whether that's down to resource requirements, whether it's impossible to do on a classical computer, right? In a feasible amount of time. These early milestones showed that quantum computers might be able to handle those calculations. And this kind of, again, got a lot of attention because there's actually a physical limit on like how small transistors can get. And transistors form the basis for modern computer chips, right? So a lot of the tech that we use is based on these transistors, and there's like a physical limit to how small they can get, which means there is like theoretically like a limit to maybe like how efficient we can make classical machines at solving these tasks. So it's actually really interesting. So like when the smallest transistor created to date is a nanometer. And this is, I believe this was out of Berkeley. It's still in the preliminary research phases. I think like the 2 nanometer transistor is a little bit more accessible. It's a little bit more well established. But the smallest transistor that I was able to find is a nanometer. That is 1/1000th the width of a human hair. And it's about half the size of a strand of human DNA. So there's human DNA, and the smallest that I was able to find is half that width, right? So we are talking really astronomically small scales that we have for our current levels of technology. And as we get smaller and smaller, there are additional problems that kind of arise. One is electron tunneling. This is another quantum phenomena where basically an electron can tunnel through very thin surfaces, wind up on the other side of surfaces, right? That is a phenomenon called like tunneling, right? And so as you get smaller and smaller, these quantum effects actually start to become problematic when it comes to the efficiency of our computing. So there's a limit on how small transistors can be, and that kind of put a lot more emphasis on quantum computers as a way to kind of like handle certain types of intense calculations that don't rely on this transistor-based technology. So these next two slides are a little bit more practical when it comes to, I'm a trader, how do I trade this? I wanted to focus on what types of calculations we can maybe expect or may be able to get sped up by the introduction of quantum computers. Because like I said, this does not apply to every class of problems. Like we don't necessarily get astronomical speed up for every type of problem. There are certain problems that quantum computers may be able to handle with significantly better performance and significantly better efficiency, but it's very unlikely that they would ever replace classical computers. It would be a lot more likely that classical computers and quantum computers would exist side by side, because for a lot of tasks, quantum computers are just overkill and classical computers can handle them just fine. And we don't necessarily see the level of speed up with a quantum computer for every type of problem. So they're not here to be like replacing classical computers. That's pretty unlikely. But there are certain types of problems that could get very solved by a classical quantum computer compared to a classical one. And so like one that I talked about is encryption, like cracking certain types of encryption. Like so that certain types of problems in encryption can be broken basically with a quantum computer in very, very, very fast time compared to a classical computer. So encryption and cybersecurity is one that I would maybe pay attention to as quantum computers become a bit more accessible and a little bit more understood. There's also quantum, chemical, and molecular simulations. These are classes of problems, obviously, like quantum simulations and simulations that are kind of founded on quantum interactions and quantum mechanics can be handled in a much faster and more effective way with a quantum computer, we think. And so this would aid drug development, medical research, material science, nanotechnology, textiles, like that kind of stuff. So those are maybe areas like pharmaceuticals, for example, are maybe ones that I would look at. Medical, like the expansion of the healthcare industry and medical technology. I would look at, like material science and nanotechnology are maybe some fields that would really significantly benefit from these speed ups based on what we understand about the potential of quantum computers. They also handle certain optimization problems much faster, we believe. So this would handle like finance, like risk assessment, actuarial science, pretty much anything that involves modeling risks of complex systems, energy for sure. is one that we would maybe want to take a look at in terms of like sectors or fields that would potentially benefit from these kinds of speed ups. Certain machine learning tasks, if like AI wasn't getting good fast enough, like there's certain machine learning tasks that can be benefited by quantum computers. And then search problems, like we talked about, like the unstructured search with Grover's algorithm. Pretty much any field that requires large databases and large collections of data could potentially see like astronomical increases in efficiency with a quantum computer. So this kind of extends to a lot of sectors like healthcare, finance, retail, telecommunications, logistics, but just anything that involves large databases is maybe stocks or companies or services that I would pay attention to as we start to learn more about quantum computers. The last kind of like practical takeaway I would say for traders is sort of looking at the major players. So the big, at least the big corporate names, not including like research institutions or universities, but the big like corporate names are Google, IBM, Honeywell, Microsoft, and IonQ. Like these are the big, like especially like the first couple, not IonQ, that's a little bit newer. But these names are like doing a ton of quantum research. We heard about like the Willow chip, right, is what we mentioned earlier in the segment. This is from the press release, but it performed a benchmark computation in under 5 minutes that would take one of today's fastest supercomputers 10 to the 25 years to complete, which is, it exceeds the age of the universe, right? So like that's the level of speed up that we're dealing with certain types of problems. Although I want to remember that this is coming from a private company. There's a certain level of like transparency that's associated with that. So just keeping that in mind that this is being reported by a company. This is the level of speed up that we could feasibly achieve, at least according to this report, with certain types of calculations, right? A calculation that take a regular supercomputer, like everyday supercomputer, 10 to the 25 years to complete was done in 5 minutes on this chip, according to Google. So again, with certain classes of problems, doesn't apply to every type of problem, but certain classes of problems, I mean, insane levels of speed up. At least we believe that is a possibility. Again, remembering that this is still very much in its infancy, and I don't want to like overhype. We have to be pretty grounded, I guess, when it comes to this. This is still like a very new field. We are in the infancy of quantum computers. This is just based on what we kind of understand about them so far and what their potentials are. But now I wanted to get into the fun part and maybe a little bit less applicable, but hopefully cool part, which is like, what is a quantum computer? What does it actually mean? I will say that like this is just me geeking out. Like you don't need to know what a quantum computer is, but if you've ever been interested in what it is, I'm going to try to explain it. It is a very, very complex piece of technology. It's like explaining a regular computer and how that works. Like that's just such a rabbit hole, and people spend their lives like learning about that, right? But I wanted to give a little bit of intuition about what it actually is because I think it's cool, and what the primary difference is, which is the way that these computers handle information. Okay. Primary difference between a quantum computer, classical computer, is how they represent information. And that's something that I think is neat. I'm going to try to talk about it. Make sense?
Yes.
Okay, so let's start with classical computers, classical bits. And like I said earlier, classical in this context just kind of means not quantum. Let's just take it like that. But when we think about classical machines and we think about classical bits, these are basically just units that store information in binary systems. Basically systems that have two possible states. So think true or false. There's two possible states, and the bit will have one of those values. Yes or no, off or on. When we think about a binary system, it's a system that has two different possible states, and bits are how we kind of like store information for those types of systems. And in modern computing, bits are really represented physically by either the presence of electrical charge or current. Because if we think about a computer, right, if we want to tell the computer add 2 + 2 together, a computer doesn't know what 2 is. But this is very simplistic terms, but a computer can understand the presence of voltage or the presence of not voltage, right? So when we think about like the physical representation of what a bit is in classical computing, it's really just whether or not there's charge or current, depending on what type of technology you're working on. But either, the current's there or it's not there, or the voltage is there or it's not there. And mathematically, we represent this with zeros and ones. So for example, if we want to tell the computer the number 20, I'm not going to get into why this is, but if we wanted to tell a computer, like, do something with 20, I'm feeding it in 20, we can use 10100 to represent that, which is basically current, no current, current, no current, no current, right? Mm-hmm. That's how the computer interprets information. Those are classical bits. And mathematically, we represent that with zeros or ones, where the bit's either the 0 or the 1, but those are the two possible values that it can have, right? But so these are classical bits, right? So this is how most modern computers really work, is with this classical way of storing information with these binary systems. Quantum bits, on the other hand, are a little bit more complicated. So quantum bits consist of quantum particles. These are two-state quantum systems. And there's a principle called superposition, which basically means that these quantum bits exist in a combination of 1 and 0 simultaneously. So that's a concept called superposition. It basically exists in a combination of these two possible states, in a combination of 1 and 0 at the same time. And that's a probabilistic combination, right? So we don't know if it's going to be 1 or 0, basically, until we measure it. It exists as both 1 and 0 at the same time. We're getting kind of Schrodinger's cat until we measure it. And this is a property called superposition, which quantum computers really leverage. And it's one of several properties that quantum computers leverage. But remember, in our classical computing case, the bit was either like current's there or current's not there. With a quantum bit, we're dealing with a particle that effectively encodes multiple states simultaneously in this probabilistic configuration, which is pretty different, right, than our classical bits.
Yeah.
This is a block sphere. I saw these things. I had to draw so many of these in grad school. This is like maybe for fun how you would represent that, where you have like you have a 0 at one end of the z-axis and then 1 at the other end. And our qubit, right, our quantum bit is some combination of those two simultaneously. These are kind of like representation for that. It's some combination of 0 and 1, some probabilistic combination of 0 and 1 that doesn't kind of pick 1 until you measure it. But when you measure it, you get the 1 or the 0. That's like, I've heard so many goofy ways of explaining that, but that's effectively what it is. It's this quantum concept called superposition. Does that kind of make sense? Quantum mechanics, I will say, asterisk, is very weird and non-intuitive. It doesn't like our classical world that we understand. Which is part of why when people explain quantum mechanics, they use these like goofy analogies. But that's because it's like fundamentally so strange and different from how our classical world operates. It's fundamentally non-intuitive. So we kind of have to break away from our intuition for a little bit to be able to understand this. Okay, so there are several quantum phenomena that quantum computers like really leverage to get these levels of speedups and to be able to execute quantum algorithms. Superposition, right, is one of them, where you have a quantum state that exists as this simultaneous combination of multiple states until it's measured. Entanglement, which I'm not going to talk about, but it's a really cool principle, basically, where two particles become correlated even when they're separated across distance. Like if I have two entangled particles and I have one over here and one on the other side of the world, if I poke one, the other, it's a very cool principle that is like, this is just sci-fi level shit, which is the process by which a quantum system kind of loses its quantum behavior due to interactions with the environment. So for example, like I said, this qubit is a mix of 0 and 1. It's a combination of 0 and 1 until I measure it. When I measure it, it picks 1, basically, right? And this kind of is attributed to this property called decoherence. It's when the quantum state sort of interacts with the environment and loses some of its quantum behavior. And then interference, which this is a big one. If I had to pick two big ones, it's superposition and interference. Interference is basically this phenomenon where probability amplitudes for super quantum state and superposition can either constructively or destructively interfere with one another. And I'll talk about what that means in a second, but that's effectively, if we think of like, quantum states in superposition as these probabilistic states, interference is these sort of, I want to say like probability amplitudes interfering in a way where they can either sort of amplify or diminish certain probabilities. I'm going to look at an example of like, hopefully like show why we can achieve speed up with these properties. If you're ever actually interested in it, like IBM has a lot of resources on this, has a lot of resources on like, what is quantum computing? Why does it matter? Why does quantum mechanics, like, what are these properties? Dives into it a whole lot more. So I'd recommend checking that out. But hopefully the example will at least help this make a little bit more sense. Well, let's start with a lock. Okay, we're going to start with a lock. Suppose we have a classical lock. Okay, and that can be opened with a combination of 4 classical bits. So we put in some combination of 4 bits. Remember, the bits are either 0 or 1 in our mathematical representation. And one of those combinations will be correct and the lock will open. Okay, so if we're dealing with classical bits, right? There's 16 different combinations, because remember, there's 4 bits that we got to send into it, and there's 2 possible states that the bits could be in, 0 or 1. So we have to now make these bit states and feed them into the lock sort of one by one. So we're going to start with 1111 into the lock, see if it opens. 1110 into the lock, see if it opens. 1111, see if it opens. We have to do this one by one, and if we try these 16 different combinations, one of these will open the lock. Okay, but that's our process for opening it. Okay, make sense?
Yes, this makes sense.
Easy peasy, right? But now let's get a little weird. Let's suppose that we have a quantum lock, and instead we have to open the quantum lock with a specific combination of qubits, right? And we're going to use 4 qubits in this case. So instead of dealing with our classical lock, where we have to make these 4 different states, send them in, or make these 16 different states of 4, send them in one by one and see which one opens the lock. Instead, we have a quantum lock that can be opened with 4 qubits. So because our qubits exist in a superposition, because they kind of like exist as this probabilistic combination of different states, what this actually means is that our 4 qubits exist in all 16 combinations simultaneously. So think about these 4 particles that have these 16 different, states kind of encoded in them in a way. And when we send them into our lock with a quantum algorithm, we can use the property of interference. Remember, where certain probability distributions, probability amplitudes interact, some increase in amplitude, some diminish in amplitude, right? We can use this concept of interference to amplify the probability of the correct combination and diminish the probabilities of the incorrect one. So now, instead of having 16 different combinations of bits and sending them in one by one, we take 4 qubits, pass it into the lock, and we can effectively, using probability amplitudes, it's existing in all 16 combinations simultaneously. And we can use this interference, property of interference, to amplify the probability of the correct answer and diminish the probability of the incorrect one. And that's the best that I can do. But like I said, the first kind of half of this presentation is really the practical, the sort of more practically applied in trading. So that's what I wanted to focus on with the takeaways. But long story short, there's evidence that quantum computers may be able to execute certain kinds of calculations that are infeasible and will remain infeasible for classical machines. And while quantum computers are unlikely to completely replace classical ones, they have the potential to achieve maybe astronomical performance increases for specific kinds of problems, such as cryptographic problems, quantum simulations, optimizations problems, search problems, and certain machine learning tasks. And this is pretty major investment from players such as Google, IBM, Honeywell, Microsoft, and IonQ, although there's a ton of other names. These are, I would say, the big players in the space. But we can't, predict traffic patterns. There's a ton of stuff about the classical world that we can't necessarily, that we don't fully understand, but we can still build technology around it. And this is, I think, a really good example of that, where we don't understand completely how the quantum world works. We're just scratching the surface. We don't even understand the full applications and limits of this technology, or what can feasibly be done with our current levels of tech in terms of building one of these things. So it's been really, really cool to see how, even without fully understanding something, we can still build potentially really major technology off of this stuff. Quantum computing, this is some sci-fi shit. And we've come a long way in a very short period of time, I will say. Yes. Like I said, this was kind of really formalized in the 1980s. Yeah. We came fast very quickly. We came very far very quickly, I should say.
Just like with AI.
And in many ways, I would kind of think about this in a similar way as AI for someone who's maybe not involved in the space as much. Because AI was kind of a similar, maybe a way where we had these very grand ideas about what the technology could do. And then as we started to really build it, we found these limitations that brought us back down to earth a little bit. Fundamentally, machine learning is kind of a means to an end. It's a way of doing what we're already doing, but better in a lot of cases. And this is another extension of that, where this is groundbreaking technology, the discoveries that could potentially come out of this, especially in physics, it was kind of originally conceived for. Yeah. It's amazing. But that being said, it's not a skeleton key solution. It could potentially improve the way that we do a lot of stuff, But similarly, it's also kind of like a means to an end. Like, how do we do what we're already doing, but better? And so I would kind of approach it with the same level of skepticism, with the same level of nuance, especially when it comes to actually like investing and being very cautious about that for sure.
It was a super interesting piece, Judah. Definitely something way new for me.